Welcome. This training video details the process of flux mapping an interior permanent magnet synchronous machine using a Unico drive and UEdit software. During this video, I will demonstrate the basic startup procedure for an IPM motor, highlighting the flux mapping process and verifying the results. First, we need to establish communication to both the DSP module, part number 326756, and the DCR5 module, part number 329039. Communication to the DSP module will be necessary to control the drive through UEdit and perform the flux mapping process. Communication to the DCR5 module will be necessary to extract the flux mapping results and analyze the data. For this, you will need two different sets of Unico serial communication kits, part number 714070. For communication to the DSP module, connect the RJ45 serial cable to the serial hub located on the front of the drive cabinet. Similarly, for the DCR5 module, connect another RJ45 cable to the isolated serial hub located within the drive cabinet, part number 329741. Make sure to connect the RJ45 connector to the master socket on the isolated serial hub. Then connect both USBs to your PC. Once the physical connections to the DSP and DCR5 module have been made, make sure there is communication to the modules via UEdit. To do this, open an instance of UEdit. Go to Communications, Connect, and select the configuration for the DSP communication. Then go to Tools, Device Identity Query, and select the device you want to communicate to. For this example, I will be communicating with device 2, which is the drive for the IPM motor. Then select Go and ensure you have communication. Next, open another instance of UEdit and connect to the configuration for the DCR5 module. Again, go to Tools, Device Identity Query, and select the device you want to communicate to. If you are unsure which device to connect to, you can open a keypad emulator in the other instance of UEdit connected to the DSP module. Go to Dictionary, Serial Com, and find the parameter called FVR DCR5 address. In this example, the address of the DCR5 module is also 2, so select this device for communication. Once communication to both the DSP and DCR5 module is established, we can proceed to the next step. There is one drive parameter that we need to change before beginning the flux mapping process. So go to the instance of UEdit connected to the DSP module. Go to Dictionary, Configure, and set Extend DPR from Disable to Enable. This adds additional functionality in the drive for obtaining accurate estimates of the D-axis and Q-axis inductance, which I will discuss later. Then perform a power reset on the drive so the parameter change takes effect. The next step is to perform the AC test for the IPM motor. But first, I'm going to open the drive diagnostic window. To do this, go to Tools, Drive Diagnostics, and select the appropriate device. Then select Go to view basic information about the drive and IPM motor. Now we will begin the AC test. From the keypad emulator, go to AC test, select Yes for synchronous motor, Enable for IPM enable, and Uncoupled for mode. For this IPM motor, the rated voltage is 281 volts, the rated frequency is 240 Hz, the rated current is 40 amps, and the rated speed is 3600 RPM. Select Yes if you have a regen drive or dynamic brake, and the default ramp time of 6 seconds is OK. Now there is a list for each portion of the AC test which I will go through individually. Select 2 for the calibration test, then select 1 to perform the calibration at speed. Following the prompts, turn the motor on. Once the motor is on, the drive will rotate a current vector at 1/4 of the rated frequency and 1/2 of the rated current. As you can see through the drive diagnostic window, the motor velocity is at 900 RPM, which corresponds to 60 Hz, and the motor current is at 20 amps. The moving calibration is more accurate than the other calibration, so this method is preferred for the IPM startup procedure. Please note that the moving calibration may take several minutes to complete. Once complete, the drive will automatically turn the motor off. Then follow the prompts and select any key to exit out of the moving calibration. Next, select 3 for the leakage test. Once the motor is on, the drive will estimate the stator inductance. Again, select any key to exit the leakage test. Next, select 4 for the stator resistance test. Once the motor is on, the drive will estimate the stator resistance. Again, select any key to exit the stator resistance test. Next, select 5 for the phasing test. The ID amps is used for a static alignment, which is run after the phasing test. Once the motor is on, the drive will rotate a current vector at 1/2 of the rated speed and 1/2 of the rated current. Unless the encoder feedback is in the DSP module motor socket, select No when asked to verify motor feedback. The drive will then confirm the number of motor poles and the feedback direction. Select 1 if the motor is moving in the forward direction, and 0 if the motor is moving in the reverse direction. The drive will automatically invert the appropriate parameters to accommodate the reversal in direction if that is selected. Next, the drive will perform a static alignment in case the phasing was reversed, as this affects the vector offset. Once the motor is on, the drive will apply a current in one of the motor phases to align the rotor. The drive will use ID amps unless the entered value was less than 1/3 of the motor rated current. In this case, the drive is using 1/3 of the motor rated current, as this is larger than 10 amps. Next, select 6 for the alignment test. Select 1 to perform a back EMF alignment test, and then select 0 to perform the test with the drive off. This specific test requires a load motor to spin the IPM motor, so enter a speed at which to perform the test. This speed should be less than or equal to 1/2 of the rated speed. For this demonstration, the IPM motor is coupled to an induction motor that's controlled through device 1. So set the velocity command of the load motor to 1000 RPM using another keypad emulator. Then turn on the load motor. Once the IPM reaches 1000 RPM, the vector offset in the forward direction is measured. Follow the prompts and set the velocity command of the load motor to negative 1000 RPM. After the vector offset is measured in the reverse direction, follow the prompts and stop the load motor. The drive averages the two measurements to determine the final vector offset. After performing the back EMF alignment test, verify the results using the drive diagnostic window. To do this, run the load motor at negative 1000 RPM and view the Q-axis and D-axis flux feedback. If the vector offset was determined correctly at no load, the majority of the flux feedback should be on the D-axis as shown here. Then run the load motor at 1000 RPM and verify the flux feedback is primarily on the D-axis again. Next, select 7 for the torque test. Once the motor is on, the drive will estimate the magnet flux and the torque constant. In addition, the drive will update the motor rated voltage. Select 1 to update or 0 to keep original value. The calculated rated torque and power of the motor is also displayed on the screen. Press any key to exit the torque test and then select Escape to exit the AC test. The next step is to obtain more accurate estimates of the Q-axis and D-axis inductance to tune the current regulators. The load motor is already spinning the IPM motor at 1000 RPM. From the keypad emulator, go to Dictionary, Application, and set I command mode equal to IM phase. Make sure that IQ IM source and ID PH source equals internal. In this mode, the drive is controlling the magnitude and phase of the current vector as opposed to the individual D and Q axes. So set the internal current magnitude equal to 10 amps RMS and the internal current angle equal to 45 degrees. Turn the IPM motor on and verify that current feedback matches the command in the sub-monitor of the drive diagnostic window. Next, open another instance of the keypad emulator. Go to Dictionary, then scroll down, then go to TorqueCal, and scroll down until the following parameters are shown on the screen. These are the torque, current, flux, and inductance measurements. Set the torque sampler from disable to enable. The drive will average the following parameters over the duration specified by torque sample time. The most important parameters for this test are the LQ mean and LD mean, which are the Q-axis and D-axis inductance estimates. Next, step up the current magnitude until the motor rated current is obtained. Once at the motor rated current, enable the torque sampler again. The estimate of LQ is 3.47 millihenry and LD is 1.84 millihenry. Run the torque sampler again to verify the results. Then bring the current magnitude down and turn the IPM motor off. Also, turn the load motor off. The next step is to use the LQ and LD estimates for the current regulator tuning. From the keypad emulator, go to Dictionary, Drive Setup, and set DSV L linking equal to disable if not already done. Then set DSV LQ and DSV LD to the estimates obtained from the torque sampler. In this example, I have values slightly below the estimates to prevent overtuning the current regulator, which could result in current oscillations. The next step is to open a data sampler that will record the results of the flux mapping, as this is important for troubleshooting purposes. Go to the other instance of UEdit connected to the DCR5 module. Ensure communication with the DCR5 module using the Identity Query window. Then go to Tools, Data Sampler. Select the Create a New Data Sampler Manager checkbox. Select Retrieve the Data Sampler Manager from the device and make sure the correct device is selected from the drop-down list. After the data sampler has been uploaded, select Finish. Select Go on the Data Sampler Manager and turn on the AC Servo Reg Flux Identity Data Sampler. Select Record to File icon at the top of the window and save the file in a desired location. Make sure that the data sampler indicates that it is recording. Once the flux mapping process begins, this will record all the data points for troubleshooting purposes. The next step is to begin the flux mapping process. Go back to the Setup menu, then select Flux IDQ Identify. Enter the maximum current of the motor, the current ramp rate, and the speed at which to perform the test. Then enter the settle time and the sample time. The default values for these are usually okay. Enter the dwell time, which is the duration the drive waits in between test points to allow the motor to cool. Then select 2 for FDQ motoring. Enter 0 for ID index and 0 for IQ index to start the flux mapping from the beginning. Follow the prompt from the keypad emulator and ramp the load motor to 1000 RPM. Again, follow the prompt to turn the IPM drive on and begin the flux mapping process. The drive will begin going through 374 different current commands, measuring the D-axis and Q-axis flux for each test point. Currently, the D-axis current command is 0, while the Q-axis current command is being incremented up to the maximum current entered previously. This can be seen in the sub-monitor of the drive diagnostics window. The flux map being created is a function of both ID and IQ. Thus, the D-axis and Q-axis flux tables are a 20 by 20 grid based on the ID and IQ index. In order to pause the flux mapping at any time, simply turn the IPM motor off. The drive will remember the last measured test point and begin at the next test point once the IPM motor is turned back on. For this demonstration, I have skipped ahead towards the end of the flux mapping process. As shown in the keypad emulator, when the ID index is 19, the last IQ index is 10. This is because the magnitude of the current vector would significantly exceed the maximum current entered previously. This is also why there are only a total of 374 test points instead of 400 for the 20 by 20 flux tables. Once the flux mapping is complete, press any key to quit. The next step is to create the IDQ command tables based on the measured flux maps. In the keypad emulator, select 1 for IDQ Maker. Enter the bus voltage for the IPM drive. Then enter the maximum speed of the IPM motor. The drive performs a quick calculation to create the IDQ command tables. Again, press any key to quit. The next step is to save the data from the DSP module. First, close all the keypad emulators in the drive diagnostic window to increase the serial communication bandwidth. Then go to Tools, Upload Device Archive, and select the appropriate device. Select the text file format and then select the IDQ command table, torque max table, and FDQ table checkboxes. Rename the archive file and browse to an appropriate location to save the archive. Then select Archive. Once complete, select Done. The next step is to save the data from the DCR5 module. So go to the other instance of UEdit. Select Stop on the Data Sampler Manager. Then go to the Remote File Explorer and select the appropriate device from the drop-down list. Click the plus icon and go to the location labeled FOD disk. Right-click on the IDQ map report text file and select Copy As. Browse to an appropriate location to save the file. Once complete, select OK. The next step is to analyze the data using the IPM spreadsheet provided by Unico. In the IPM spreadsheet, navigate to the Setup sheet. Since only motoring flux map was generated, select the motoring checkbox. Then select the VBus checkbox for bus voltage. Lastly, select the appropriate checkbox based on the version of the drive software. All the drive parameters highlighted in yellow will be updated from the IDQ map report file, except the maximum current. So select the Import IDQ map report button and navigate to the file saved from the DCR5 module. Next, select the Import Flux Table Archive button and navigate to the archive file taken from the DSP module. Lastly, select the Import IDQ Command Table Archive button and navigate to the same archive file. As you can see, the drive parameters were updated from the IDQ map report file. Now I will highlight the important sheets in the IPM spreadsheet. The FD sheet shows the D-axis flux table as a function of the D-axis and Q-axis currents. Similarly, the FQ sheet shows the Q-axis flux table as a function of ID and IQ. The ID entry sheet shows the D-axis current commands as a function of torque and speed. Similarly, the IQ entry sheet shows the Q-axis current commands as a function of torque and speed. The torque max sheet shows the maximum torque for a given speed. This is the derived torque speed curve, and you can see the maximum torque decreasing with speed. The chart sheet graphically shows the IDQ command table with the current, torque, and flux constants. The green lines are the constant current curves. The blue lines are the constant torque curves. The red lines are the constant flux curves and represent the voltage constraints at higher speeds. The black line is the max torque per amp MTPA curve used by the drive below base velocity. At higher speeds, when the drive runs into voltage limits, the IDQ commands follow the flux constant curves. Lastly, the orange line represents the torque max curve shown in the previous sheet. An additional step in analyzing the data is to ensure there were negligible errors in the current and torque during the flux mapping process. So open the DCR5 data sampler file in UEdit. As you can see, I only have 56 samples as opposed to 374 because I skipped a portion of the flux mapping process. Regardless, right-click one of the data points and select Export. Select All Acquisitions to export all the data points. Also select the Export First Acquisition header only. Rename the file to something appropriate, and then select Save. Next, go to an Excel spreadsheet and open the recently saved text file. You may need to select the Refresh button until the file appears. When opening the text file, make sure to select the delimited checkbox and then select Finish. In the spreadsheet, you can see the following variables saved via the DCR5 data sampler: DX is current request, QX is current request, DX is current feedback, QX is current feedback, DX is flux feedback, QX is flux feedback, torque calculation, Unico's torque estimation, torque transducer feedback, velocity feedback, and bus voltage feedback. If you have an earlier version of the DCR5 data sampler in which the torque calculation is not logged, it is simply the product of current and flux. More specifically, the torque calculation equals 3/2 times the pole pairs times the difference of D-axis flux times Q-axis current and Q-axis flux times D-axis current. Since the current feedback is logged in units of amps RMS, we need to multiply by the square root of 2 to convert to units of amps peak. The units of the torque calculation are in Newton meters. Anyways, next check there was no significant errors in the D-axis current, Q-axis current, and Unico's torque estimation. The ID error is the difference between the request and feedback. Similarly, the IQ error is the difference between the request and feedback. Lastly, the torque error is the difference between the calculation and the feedback. Visually check the spreadsheet calculations to ensure there are no significant errors. It is important to check these errors, especially when troubleshooting the IDQ command tables. The next step is to configure the drive to use the IDQ command tables. So go to the instance of UEdit connected to the DSP module and open a keypad emulator. Go to Dictionary, Application, and set iCommand mode equal to IDQ table. Based on the velocity feedback and torque command, the drive will command the appropriate D and Q axis currents. The last step is to verify the IDQ command tables. For this demonstration, I will be commanding 7.64 Newton meters of torque at 1000 RPM. So go to the IPM spreadsheet and then the ID entry sheet. Based on the ID command table, the D-axis current command is negative 2.25 amps RMS below 4000 RPM. Then go to the IQ entry sheet. Similarly, based on the IQ command table, the Q-axis current command is 7.41 amps RMS. Before providing a torque reference for the drive, verify the max torque scalar. To do this, go to Dictionary, Drive Limit, and find the parameter called max torque scalar. This is 100 Newton meters for this drive. Next, go to Dictionary, Application, and verify that the torque source is internal. Set torque internal equal to 7.64%, which will correspond to 7.64 Newton meters. Turn the load motor on to regulate the 1000 RPM set point. Then go to the sub-monitor in the drive diagnostic window to view the Q-axis and D-axis current feedback. Turn the IPM motor on and verify the Q-axis current feedback and D-axis current feedback. As you can see, the IQ current feedback is 7.4 and the D-axis current feedback is negative 2.2.
For more information on this topic, please go to www.unicous.com